Much like a top Michelin star chef, a supply chain scientist has to create recipes that adapt and evolve to every scenario. As such, today we're going to investigate what it takes to create these recipes, and in particular, what characterizes the ones we use in our supply chains. So Joannes, we've used kind of this term, numerical recipes, a few times before. So why did you think it was important to revisit it?
This term, I stole it, from people that in the 80s wrote an incredibly successful book called Numerical Recipes. And it emphasized a certain way to look at the problem. And you see, there is this, we've made already an episode on naive rationalism. There is this idea that usually you have a problem and you have a solution. But the reality is not as simple. Usually the type of solution that you have literally shape the problem and vice versa. So you have things that are going back and forth, and you have kind of a trade-off in the way you want to approach your problem depending on the way you approach your solution. So all of that is maybe a bit fuzzy, but the key idea is at Lokad, we want to deliver, numerical results for companies who run actual supply chains. And the problem with, I would say, other terminology, we could say we use algorithms, or we use machine learning, or we use, the problem is that it emphasizes as if there was something that was like completely objective, completely well defined, where you have something which is binary. You have the problem, you have the solution, and then for the same problem you can have solutions that compete. But the reality at Lokad, it's usually when you want to basically deliver results for an actual supply chain, the whole thing is a lot more muddy. And it's a very accidental process where you have many bumps along the road, and what you get in the end is literally something that has, I would say, a lot of complexity. Hopefully most of it is only reflecting the complexity of the real world. Some of it is just accidental complexity. So what you get in the end is this kind of numerical recipe which describes all the chain of numerical computation to get the results.
So why is it that something like an algorithm wouldn't be appropriate to kind of describe that? I mean, what is it that an algorithm kind of misses out?
I'm using the term recipe precisely to say this is not an algorithm. And this is something I would say for maybe a public, if by any chance you've done, a master in computer science or a master in machine learning, you will have learned in your textbooks and through your courses that you have algorithms. So let's say if we take, the archetype of the algorithm, the sorting algorithm. So you have a collection of objects with an order relationship, and you can sort them. And you have algorithms that are well-defined, series of steps, so that you start with a collection of objects that is not sorted, and at the end, the collection is sorted. And your algorithm is going to have many properties, such as the memory consumption, the complexity, which is the number of steps, and you can have, there is a word, by the way, bestiary of sorting algorithms that have different properties. Some of them are deterministic, some of them are stochastic, some of them are already very, very good if the data is already partially sorted, some etc., etc., etc. But the thing is, this is the sorting algorithm. This is a super well, a super clear-cut situation where you have a problem statement that is completely non-ambiguous. So you want to sort a collection of elements given an order relationship. It has like a mathematical clarity to it. On the contrary, when you think about what is the sort of problems that you need to solve in actual supply chain situations, it's very muddy. I mean, you have MOQs, but MOQs, they are not like the laws of physics. They are more like the result of a negotiation with your suppliers. So if numerically an MOQ proved to be really a problem, maybe you can actually make a phone call with the supplier and arrange something that is in between. So you see, it's and maybe a smart numerical recipe will capture this sort of option that exists in the real world, but suddenly it doesn't have this kind of almost like crystal-like purity to it.
Okay, so what you're kind of saying is the use of an algorithm is better for when it's maybe a more clearly defined problem with maybe a definite output, but something like a numerical recipe is more for something that's a bit more muddy, and that's why it kind of works so well in supply chains.
Exactly. I mean, at Lokad, make no mistakes, we use like every single, serious or semi-serious software company out there, we use tons of algorithms. The Lokad stack is literally a very long series of algorithms, and because the way we have engineered, Lokad around a domain-specific programming language called Envision, our compiler is like an endless series of algorithms first that transform, the script itself into abstract representation, down to the series of execution for the compiled program that needs to be executed, etc., etc. So there are, I would say, algorithms are all over the place, and that here lies the danger. Is that again? That's a danger, just like naive rationalism. That is, it's not a danger to the uneducated audience. If you had the privilege of having never completed a master in computer science, that you're not a software engineer professional, this is probably not the sort of problem that you will face. But for the problem is that if you happen to be very educated in these sort of things, what you've been taught, in classes, what you're reading in most computer science books, gives you a very distorted vision of what problems really look like in real supply chains. So algorithms are very, very useful. It's very, very good that Lokad, for example, can rely on, by the way, we use a whole collection of sorting algorithms that have pros and cons that are completely well understood thanks to decades of, of research that have laid out a completely, I would say, an extensive, mapping of all the various, dimension for this tiny problem. But it's just that, it's like you have a very complex machine, and you achieve perfection for a tiny cog. So yes, if you look at one screw, and you would say, what is the optimal metal for this screw? And because you have a problem that is so well defined, so narrow, you might have an answer which is you need to use exactly this type of steel for this screw because it's completely optimal with regard of all the constraints that you have. But then, is having the screw at this place in the machine optimal, to solve the big problem? Probably not. Again, it's not because you have optimality into a one tiny detail of your massive setup that the whole contraption, when you put everything together, really makes sense. And that's and when you go into the real world and you want to solve supply chain problem, I would say you end up with numerical recipes rather than algorithm. Again, it's kind of the same, except that the emphasis and the attitude of the person who are, crafting the thing is not the same.
Okay, let's talk a little bit more about the actual person that's creating these numerical recipes. Seems very kind of subjective, and it's very kind of dependent on the scenario. So kind of how reliant are you on the kind of the skills and the expertise of that supply chain scientist?
Quite a lot, actually. Quite a lot. And that's something that should not be neglected. You see, when you look at an algorithm, you would say it's completely objective. It's literally a mathematical framework. You have proof. You have a perfectly well-defined. It's literally a branch of mathematics. I mean, algorithms are a branch nowadays of mathematics. So it's the pinnacle of, I would say, objectivity. I'm not saying that objectivity do not exist. A lot of people have taste about, the aesthetics of algorithms. You can write it in ways that are vastly more elegant. So it's not like compared to others. So it's not like subjectivity do not exist. Subjectivity exists very much, even in mathematics. And if you actually talk with a mathematician, they will tell you that there is things like elegance that are really driving, the way they look at things. But if we go, to numerical recipes, it's literally the idea that you can objectivate, you can make objective everything. I believe it's again another bad case of naive rationalism. There are plenty of things where the reality is too complex to fit in any kind of mathematical framework that we know of. We just don't have the tools. Maybe in some distant future when we have some kind of AI or whatever, but at the present time we do not. So at some point you have like something that you try to quantify, and yes, you can extract patterns from the data using statistics. By the way, all the machine learning methods that we know at present day are glorified statistical tools to deal with high dimensional data. So you have some bits where you can use relatively sophisticated methods, but there are a series of steps where you will have to do judgment calls. For example, how do you deal with this COVID situation from a supply chain perspective? I mean, obviously, it does not. I mean, you do not have prior example in your sales history. So at some point, and that the decision that needs to be made in your supply chain at present time need to take into account this very bizarre situation. And so there is no alternative but to have, I would say, a smart, supply chain scientists that happen to have like a good grasp of what is actually happening in the supply chain and make judgment call about how those things should be reflected numerically in the system. And thus, just like this chef metaphor, at some point, it's not because the choice of the way you do your exact recipe is super highly subjective, that at the end of the day you don't end up with on crappy chef on one side and incredible other I would say chef of incredible talents on the other side. Even if you cannot define clear-cut rules that let you sort out which are the good ones, the bad ones, clearly the extremes exist nonetheless, and people that are educated to some extent, they can make a judgment call about who is a great chef and who is a crappy chef, and the extreme are fairly obvious. And if you want to have all the nuance in between, you will probably need to have more skills yourself and be versed into the culinary art and cooking. But you see, this is fairly rational to proceed like this.
Okay, let's stick with kind of the Lokad kitchen then. For kind of our company, we've got a wide range of different clients, lots of different industries, lots of different scenarios, lots of different kind of contexts. How do you ensure then that you've got lots of different supply chain scientists all creating their own kind of numerical recipes? How do you ensure that the quality of those recipes that are created at the end are all kind of up to scratch and are all up to a good level?
So, I mean, there are so many angles to this question. I mean, first, you need to make sure that you don't betray the business. The biggest danger when you put, a smart engineer in front of a problem is that the engineer, it's by training, will always come up with a formula that looks like a very profound and very scientific. So, and again, I believe there is a saying that says that there is like a free path to ruins. The most enjoyable path is women. The fastest way to ruin is actually gambling. But the surest way to ruin is to hire more engineers. So first, you need to make sure that you have alignment in terms of vision between the problem being solved and all the sophistication, in the quantitative modeling that is being applied. That's the first thing. And by the way, this is also why at Lokad we cultivate, having a lot of materials on our website, on YouTube, in many places, is that we need to cultivate this understanding of the problems themselves. So that's the first thing, is alignment, between the technique and the business. The second thing is you need to have a tooling that minimizes the amount of daily food gunning taking place. Food gunning is just you have a gun in your hand and you shoot your food, and literally those things tend to happen over and over and over, especially when you start dealing with, I would say, fancy numerical recipes. What do I qualify as fancy? I mean, there are plenty of companies that say, oh, we use like TensorFlow. Yes, excellent. So now you've just acquired 100 more ways to shoot a bullet in your feet. And some of those ways are you can be exceedingly, I would say, creatives, and you can have like a lot of surprise going on, etc. So business alignment first, and then you need to have a tooling that by design, gives you a high degree of correctness. That's, correctness by design. It's something that is very, very prevalent in terms of thinking at Lokad, because although I'm a big believer in education, I believe that, it's best when by design, people can be allowed to be idiots. Again, we hire smart people, but even smart people happen to have, bad days. They happen to have once in a while, they didn't sleep very well. So you want to have a tooling that, prevents you from doing super dumb terminal mistakes, so that supports you to be, smarter even when you're just too tired to be smart. And then maybe the third idea is that you need to engineer plenty of processes. And for example, at Lokad, I would say half of Lokad is really about the know-how of how to roll out a quantitative supply chain initiative. And when you say roll out a quantitative supply chain initiative, is, for example, how do you end up with numerical recipes that don't have terminal problems? And when I say terminal, I mean something that would, just kill the initiative because the problem is so big that people decide rightfully that actually killing off this initiative is the best way forward. And then what sort of problems could you have? Yes, the numerical recipes can be bad, but in so many ways. It can be bad because in terms of variance of compute time, it's way too erratic. So sometimes you run the damn thing and it takes 1 hour, sometimes it takes 8. People are not exactly sure why. That's a big problem. It can be bad because, for example, it's pretty opaque. And by the way, when this black box effect usually is, it's very difficult to have something that is both numerically smart and that is not like an immediate black box, including for the supply scientist herself or himself. And then you can have sometimes, how do you prevent, you can have numerical stability problems where on average your recipe is excellent, but in 0.1% of the situation, it's downright insane. And that creates a lot of problems, operational problems for the companies, because again, supply chain costs tend to be concentrated on the extreme. When you're roughly right, it's just fine. But if you're downright insane, you can literally have a big operational problem that shut down, a factory or warehouse.
Okay, let's talk a little bit more about maybe the supply chain industry itself. How much have you seen them kind of companies in that industry kind of implementing numerical recipes themselves? Or would you say that the majority of people and companies are kind of still stuck in that kind of classical algorithm kind of based approach?
So first, the funny thing is that the vast majority of companies operates, I mean literally all of them actually, through recipes. Because this, I would say, algorithmic thinking, it's a recipe for some kind of data science disaster. So actually, there is a lot of hypes, but there is basically nothing in production. So everybody operates in practice through numerical recipes. And 90+%, of the market shares is just Excels. But people look down on those Excel sheets saying, it's just Excel. No, it's not just Excel. It's the embodiment of the understanding on how you should actually model quantitatively your supply chain. So those Excel spreadsheets, they are literally the numerical recipes. And they are the reified version, of those recipes. And in this respect, it's quite good. Where it's not so good is that the spreadsheets, in general, it doesn't matter if it's like a spreadsheet on a desktop or on a web app, it doesn't matter if it's like offline or online. Spreadsheet or the tabular thinking is not exactly suitable to solve supply chain problems. So you see, my big criticism is that the tooling is inadequate. You can't deal with uncertainty. You can't deal with cannibalization. You can't deal with multi-echelon supply chain. There are so many problems that literally don't fit in a spreadsheet, no matter how you package the spreadsheet. So my criticism is not that the problem with spreadsheet is that it's those are, I would say, numerical recipes, that are highly subjective, includes a lot of know-how. This is not part of the problem. This is literally part of the solution of the problem. My criticism is that this tooling is usually inadequate. But you see, that's something that is, and typically, present-day companies, they operate through numerical recipes, but they don't acknowledge that this is a good thing, and this thing is not going to go away. This is literally the very reasonable, proposition to address the supply chain problems. But the problem that they face is inadequate tooling and frequently inadequate processes, such as, for example, this divide and conquer, problem that we discuss with silos, where people can be, for example, trying to deal with pricing on one side, planning on the other side, or while it's literally the two sides of the same coin, as discussed in the last episode, etc. But you see, numerical recipes are here to stay, and and my position is that it's literally the right mindset whenever supply chain problems are involved.
Okay, we'll start sort of wrapping things up then. So kind of what is the main conclusion of today's episode? Why is it that numerical recipes are so important, and why is it so important to kind of change that mindset?
I believe it's literally numerical recipes are the embodiment of this other line of thinking, which is it's better to be approximately right than exactly wrong. So you will end up with formulas that don't have purity. They are not like I would say electromagnetic equations where you have those super neatly defined, where you can define the 4 Maxwell equation. Within 4 equations you can define everything that happens in terms of electromagnetism. It's incredibly pure and tight. Supply chains are not like that. Supply chains, your numerical recipe is going to be hundreds of semi-accidental, conditions, factors, twists, so that the whole thing makes sense, so that the whole thing is approximately correct, doesn't do any things that are completely insane, so that those things are highly predictable, so that you don't have like too much surprise. Ideally, very little amount of surprise in the numerical outputs of your recipes, and that having something that can be just like a recipe, it should be also versatile, just like a big chef. Remember those emissions. You want to do a dessert. You know what? I'm not going to allow you to use sugar today. Oh crap! I want to do dessert. How am I going to do a dessert without sugar? That's that's the sort of things. You need to be super agile, so that if there is something missing, just because you had like weird condition going on, like a pandemic, you're not you have a way forward. And by the way, that's very interesting, because those Top Chef emission, I give you either you're short on time, if you have only 30 minutes to prepare something that normally would take like 4 hours, or you're short on ingredients, or you're short on tools, or you're short, and yet you need to find a way forward. And that's again, I believe that's what those recipes look like. I mean, you have weird constraints that are changing over time. It comes with a degree of surprise, and the real chef is the one that can literally improvise. But if you watch closely those emissions, you would see that there is a method to it, and that's really that differentiates the great chef. The great chef is not somebody who is going to do random things when facing a missing ingredient or a very short timeline. You can really see that there is literally a decade of experience of how to cope with this mess. There is a method to it, and that's exactly the sort of things that we cultivate at Lokad.
Okay, we'll have to wrap it up there, but I think that analogy of Top Chef is one that's really kind of powerful, and definitely one we can relate to in this office. Got many fans of that. So that's everything for this week. Thanks very much for tuning in, and we'll see you again in the next episode. Thanks for watching.